The coldest edge of home hides a fever hot enough to sound invented. You would expect the dark beyond Pluto to fade into emptiness, not tighten into a border measured in tens of thousands of degrees. Stay with me, because this is one of those space stories that sounds fake until the numbers start landing. But first, subscribe if you want more science stories that take giant ideas and make them feel clear, close, and unforgettable. Far from Earth, where sunlight is weak and the sun is only a hard white spark, two old spacecraft kept moving. They were not chasing glory anymore, they were listening. And what they found at the edge of the sun's reach was not calm, not simple, and not small. People call it a 50,000-degree wall. That phrase sounds like the end of everything. It sounds like a ring of fire wrapped around the solar system. It sounds like one bad step would turn metal into smoke. That is not what scientists mean. The wall is not a solid wall. It is a region of plasma, which is gas so energized that its atoms lose electrons and become charged. And yes, it matters, because it sits at the edge of the giant bubble that helps shield our world. The weird part is not just the temperature. The weird part is where it shows up. This is the outer dark, the place most people imagine as the most empty and lifeless part of our neighborhood. Yet that is exactly where the story gets tense. Out there, the sun's influence does not end with a neat line. It frays, it bends, it presses against the material between the stars like breath against a window on a winter night. And when that pressure changes, the shield around our solar system may not behave the way we once thought. That is why scientists still watch these results so closely. Not because Earth is about to be burned by a cosmic furnace, because the outer skin of home may be hotter, leakier, and stranger than expected. Now let us start from the beginning. Most people think the solar system ends where the planets end. That feels obvious. It is also wrong. Neptune is not the true border. Pluto is not the true border. Even the icy debris far beyond them is not the real ending point. Those are objects inside the system, not the edge of the sun's full reach. NASA says the real outer bubble is called the heliosphere. It is built by the solar wind, a stream of particles blowing outward from the sun. That wind carries pressure and magnetic fields far beyond the planets. So the true edge is where that outward push runs into interstellar space and stops being in charge. That means the boundary is not paint on a map. It is more like surf meeting a shore. The waves still move, but they break, drag, fold, and push back. Space at the edge of the sun's bubble behaves that way too. Before Voyager made this famous, the heliosphere had a public relations problem. It sounded dull. Jupiter had storms bigger than Earth. Saturn had rings. The heliopause sounded like paperwork at the bottom of a science handout. Even the Voyagers were underestimated. Voyager 1 and Voyager 2 launched in 1977 to visit the giant planets. They were built for a grand tour, not for a second life, as old-age scouts touching the boundary between our star and the galaxy. By the late 1980s, many people felt the headline years were over. But underdogs do something flashy stars do not always do. They keep going. NASA says the Voyager interstellar mission continued after the planetary mission ended in 1989. The planets had been the first act. The first surprise came long before either spacecraft fully crossed the edge. Scientists expected the solar wind to slow as it pushed into the outermost region of the sun's bubble. NASA says Voyager 1 crossed the termination shock in December 2004 at 94 astronomical units. Voyager 2 crossed it in August 2007 at 84 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. That is about 93 million miles. So 94 astronomical units is about 8.7 billion miles. That is like stacking the Earth-Sun gap almost 100 times. Scientists expected a slowdown. What they actually found was a whole messy transition zone called the heliosheath. That is the outer layer of the heliosphere, where the sun still has influence, but not total control. The simple border turned out to be a crowded hallway, not a clean doorway. Think of opening your front door on a freezing day. The house is still warm, the outside is still cold, but the doorway itself is a swirl of both, where air, sound, and smell all mix. That is a good way to imagine the heliosheath. The second surprise was emotional as much as scientific. The farther the spacecraft went, the more we realized the edge of home was not distant scenery. It was a working shield. JPL said Voyager 1 showed the heliosphere protects Earth and the other planets from more than 70% of cosmic radiation. That one number changes the mood of the whole story. More than 70%. That is not decoration. That is not background. That is a filter standing between our neighborhood and a harder galaxy. Cosmic rays are high-energy particles, often linked to violent events like exploding stars. They are not movie beams. They are tiny and real. Over time, they can damage electronics, stress instruments, and matter a lot for living bodies. So when people hear 50,000-degree wall, the useful question is not, will it burn us? The useful question is, what does this boundary tell us about the shield around us? That is the adult version of the headline, and it is much more interesting. Voyager 1 reached the heliopause, the boundary where the sun's bubble gives way to interstellar space, on August 25, 2012. NASA says it was about 122 astronomical units from the sun. That is roughly 11 billion miles. It became the first human-made object to enter interstellar space. But the crossing did not arrive with fireworks. There was no bright line, no glowing gate, no giant alarm in mission control. In fact, scientists nearly had to solve it like a mystery after the moment had already passed. They expected Voyager 1's plasma science instrument to help confirm the crossing, but NASA says that instrument had stopped working in 1980. The cleanest witness had gone silent decades earlier, so the team had to listen another way. That is where the story gets beautiful. It becomes less like watching a rocket launch and more like hearing a floorboard creak in a dark house and knowing someone has entered the room. Science can feel like that. What scientists expected was a clear, direct measurement. What they actually found was a subtler clue. NASA says Voyager 1's plasma wave subsystem later detected oscillations in the surrounding plasma, showing the spacecraft had entered a denser region. Like hearing a room change shape by the way a note echoes, the team could tell the environment had changed. One of the names tied closely to that work was Don Gurnett at the University of Iowa. With William Kurth and others, he helped turn faint plasma signals into evidence. In Science, on September 27, 2013, Gurnett and colleagues published In Situ Observations of Interstellar Plasma with Voyager 1. That paper helped lock the crossing into place. By then, the Voyagers had become something more than spacecraft. They were old, metal listeners. Each one was smaller than a car, yet each one was touching the edge of a bubble larger than the orbit of every planet. That flip in scale matters. A machine modest enough to fit in a driveway was reporting on a frontier billions of miles wide. It is like using the tiny bulb inside your refrigerator to help map the shape of a whole stadium in the dark. Small tool, huge question. The third surprise arrived with Voyager 2. This was important because one crossing can always be a weird local event. Two crossings begin to look like a pattern. Voyager 2 reached interstellar space on November 5, 2018, according to NASA and JPL. At that moment, it was about 11 billion miles from Earth. JPL noted that light from Voyager 2 to Earth took about 16.5 hours. A text from your friend crosses a city in a blink. A whisper from Voyager crossed half a day of darkness. Scientists expected Voyager 2 to confirm the broad picture. They expected change in particles. They expected denser plasma outside the heliosphere. They expected a colder interstellar medium than the plasma inside the sun's bubble. What they did not expect was just how odd the numbers would feel. In Nature Astronomy on November 4, 2019, John D. Richardson and colleagues reported that Voyager 2 observed plasma temperatures of 30,000 to 50,000 Kelvin near the heliopause. Models and earlier observations had predicted something more like 15,000 to 30,000 Kelvin. That gap mattered. This is where the famous headline comes from. 30,000 to 50,000 Kelvin. Those numbers feel like a mistake. They feel like someone mixed up a laboratory furnace with empty space. They feel impossible beside the word cold. If this twist surprised you, what part hit you hardest? Would you leave a comment and tell me? Your comments help me see which science stories deserve a deeper dive next. That matters because this one keeps changing shape the closer you look. Now we need one important correction. High temperature in thin plasma is not the same as standing in an oven. If the particles are sparse, they can carry a lot of energy without dumping that energy into you the way a kitchen burner would. So this is not a literal firewall that would roast a spacecraft on contact. That does not make it harmless. It makes it subtle. The risk is not movie fire. The risk is what this energized boundary tells us about pressure, compression, radiation, and the changing condition of our protective bubble. Think of the difference between touching boiling soup and stepping through a room with only a few super-fast dust grains in it. Both can involve high energy. Only one feels like a burn on your skin. The heliopause story is closer to the second image. Still dangerous for physics, not dramatic for your fingertips. Scientists expected interstellar plasma beyond the heliopause to be colder than plasma inside the heliosphere. What they found did support that broad idea. JPL said Voyager 2 confirmed the nearby interstellar plasma was colder than the plasma inside the heliosphere. But it was also warmer than expected. That is a big difference. Expected colder than inside, yes. Expected around 15,000 to 30,000 Kelvin, no. Measured near 30,000 to 50,000 Kelvin, yes. The fridge was still colder than the oven, but the milk was warmer than it should have been. JPL also said the plasma outside the heliosphere appeared denser than the plasma inside. That fit earlier expectations, but there were hints of compression too. Voyager 2 saw slightly warmer plasma outside than expected, and a slight increase in density just before it crossed. Compression sounds like a dry word. Picture squeezing a balloon between both hands. The skin tightens, the air inside shifts. You start seeing where the surface stretches and where it resists. That may be happening around the heliosphere, and if it is, then the boundary is not just a line, it is a stressed structure. That matters for how the sun meets the galaxy. Ed Stone, the Voyager project scientist and a Caltech physicist, put the bigger point clearly in JPL's 2019 release. The probes were showing how our sun interacts with the material between the stars in the Milky Way. That sounds calm. But what it describes is an active collision zone. The fourth discovery was about leakage. Scientists expected the heliopause to be more like a firm border. Not solid maybe, but cleaner. JPL reported that a trickle of particles from inside the heliosphere seemed to slip through the boundary into interstellar space. That was a serious clue. If the heliosphere is our moving shield, a leaky boundary changes how we think about protection. JPL even said the region where Voyager 2 crossed, closer to the flank of the heliosphere, appeared more porous than where Voyager 1 crossed. That means the shield may not be equally strong everywhere. Think about a raincoat. A perfect one keeps the storm out. A worn one still works, but water creeps through at the seams. You do not call it useless, but you stop calling it simple. That is why this is not a small problem. Not because Earth is about to be torched by a giant wall of fire. Because our best natural shield against some cosmic radiation may behave more like a living membrane than a fixed shell. Membranes flex, they stretch, they compress, they leak. And all of that becomes important if you want to predict the space environment far from Earth, or one day send people into it for years. The farther humans dream of going, the less these details stay academic. A mission to Mars already faces radiation concerns. A mission far beyond Mars would care even more about the way the sun's shield thins and shifts. Bad models in deep space are not small mistakes. They are like misreading sea ice before a polar crossing. One wrong assumption compounds every hour. Radiation forecasts change. Electronics age faster. Communication planning gets harder. Margins shrink. And then came the fifth surprise. Scientists expected the magnetic field just beyond the heliopause to point in a different direction from the magnetic field inside. Voyager 1 hinted that maybe it did not. Voyager 2 confirmed the strange part. JPL said the magnetic field outside the heliopause was parallel to the magnetic field inside. That sounds tiny until you feel what it means. Imagine stepping out of your front door and finding the wind outside somehow lined up with the air moving through your hallway. The doorway would suddenly feel more mysterious than the yard. That result made scientists take the geometry of the boundary even more seriously. Maybe the shape of the heliosphere matters more than we thought. Maybe the local interstellar magnetic field is interacting with it in ways the simple picture missed. Maybe our first cartoons of the border were just too clean. And that is a pattern in this story. Every time scientists expected a sharp answer, the boundary acted more like weather. Not chaos, not nonsense, but layered behavior with texture, timing, and local differences. Could you tap like and tell me if stories like this make deep space feel more real to you? That little action helps the video find people who care about careful science, not just loud headlines. Because from here, the mystery stops being dramatic and becomes precise. That is where science gets strongest. Scientists will tell you they do not fully understand this yet. JPL said Voyager 1 saw slightly higher than expected plasma density outside the heliosphere. Voyager 2 saw slightly warmer than expected plasma outside it. Both results suggest compression, but the cause is not fully pinned down. That matters. Not fully pinned down is not vague mystery. It is honest uncertainty. It means the data is real, while the full explanation is still being tested. There could be several pieces in play. The solar cycle may move the heliopause inward and outward. Remember, JPL described that boundary as behaving somewhat like a lung, expanding and contracting with the sun's roughly 11-year activity rhythm. A moving edge is harder to model than a frozen one. The path of each spacecraft matters too. Voyager 1 and Voyager 2 did not leave the heliosphere at the same place. They exited at different times, in different directions, under different solar conditions. That alone can change what the boundary feels like. Then there is the fact that Voyager 2 may have crossed in a more porous region. That is JPL's word, porous. Like wood with tiny gaps, or bread full of holes, or a sponge that looks solid until water proves otherwise. That is not how most people picture the edge of the solar system. This is also where those exact dates start to feel personal. August 25th, 2012. November 5th, 2018. November 4th, 2019. These are not just calendar stamps. They are the moments when our map of home changed shape. And the tools doing that work were old, very old. Voyager 1's failed plasma instrument is part of why the first crossing had to be inferred through plasma waves and particle changes. That is like losing one ear and still learning the shape of a room by the echo of your footsteps. It also says something lovely about science. Perfect data is rare. Useful data is enough. You work with what survives. You stay patient. Don Garnett's work at the University of Iowa, Ed Stone's leadership through Caltech and JPL, Richardson's team in Nature Astronomy, and NASA's long mission updates all form part of the same scaffold. Different people, different instruments, different dates, one slowly sharpening picture. It is easy to miss how unusual that is. Most machines do not work this long. Most stories do not stay open this long. And most scientific ideas are not forced to stretch across decades before the answer begins to appear. By now, the Voyagers are farther than any other human-built objects. NASA says Voyager 1 is beyond the heliosphere, and Voyager 2 is too. They remain the only spacecraft to operate outside the heliosphere. That alone makes every bit of data precious. Imagine trying to understand the edge of an ocean with only two drifting buoys. One crosses in one season, one crosses later in another place. Each buoy can tell you the water feels different. Neither can show you the whole coastline. That is where we are. We know more than before. We know less than a full map requires. And the space between those two truths is where the caution lives. Would you share this with one person who loves space and would actually care about the real story behind the scary headline? Sharing helps this reach the right viewers, the ones who want to understand instead of just react. Because the word risk can be used badly here. Used well, it means something more useful. The risk is not that the wall itself becomes a disaster movie. The risk is that a misunderstood boundary leads to weak models of radiation, shielding, and outer mission design. If the heliosphere blocks more than 70% of cosmic radiation, then changes in its edge matter. Small misunderstandings at the edge can become big mistakes in planning, and there is a deeper human point here. We like to imagine home as a fixed place. In space, home is also a moving condition. Earth rides inside a vast magnetic and particle bubble blown by the sun. That bubble sails through the galaxy like a ship through weather. JPL used that ship image, and it works. Inside the heliosphere, the plasma is hot and sparse. Outside it, the plasma is colder and denser. But like a ship's hull under pressure, the boundary is not just there, it is being tested. That test can show up as compression. It can show up as aligned magnetic fields. It can show up as leakage. And yes, it can show up as temperatures high enough to sound absurd. There is another reason scientists keep watching this boundary. The sun itself is not steady in the simple everyday sense. Its activity rises and falls. That changing activity can reshape the heliosphere over time, the way wind can puff a tent wall in and out through the night. A changing shield is harder to trust than a fixed one. Picture camping in bad weather. If your tent holds the same shape all night, you sleep better. If the fabric keeps snapping inward and outward, you start listening differently. Every gust matters. Every seam matters. The heliosphere may work a little like that. Not fragile in a human way, not about to collapse tomorrow, but responsive, moving, and sensitive to pressure from both the sun and the interstellar medium. That is enough to keep scientists cautious. And caution in space is not fear, it is respect. If you are sending instruments beyond the planets, respect keeps them alive longer. If you ever send people much farther out, respect may keep them alive at all. There is also the simple fact that we only have 2 direct crossings. 2 is better than 1. 2 is still not many. It is like trying to understand a whole mountain range after hiking only 2 narrow trails. Maybe both trails are typical. Maybe both are weird in their own ways. Maybe one crosses rock and the other mud, and you do not yet know what most of the range feels like. That is the state of knowledge at the heliopause. So future science wants more. Better plasma measurements, better particle tracking, better models of how the sun's magnetic bubble changes through time. And maybe one day, more spacecraft crossing more parts of the boundary. That is when this story stops being about one dramatic number and becomes about a whole field of questions. How thick is the transition region just beyond the heliopause? How much does it shift with the solar cycle? Where is it most porous? How much does local galactic weather matter? Those are not tiny details. They decide how we understand our place in the Milky Way. They shape how we think about long robotic missions. And one day, they may shape routes, timing, and shielding for human voyages far beyond the inner planets. On Earth, we like walls because they feel final. This wall is not final. It is active. It is more like the skin on a living thing than the bricks of a building. Skin can protect. Skin can bruise. Skin can heal. Skin can tell you something is wrong before the deeper body feels it. That is why this outer boundary deserves attention. On one side, billions of miles, magnetic fields, and interstellar matter. On the other, a spacecraft whose power budget feels tiny by modern standards, more like a few dim household lights than some giant power plant. Tiny signal, huge discovery. You can almost hear the silence around it. No engine roar, no crackle of visible flames, just cold black distance and a faint electronic heartbeat crossing hour after hour toward Earth. That silence makes the numbers louder. 30,000 to 50,000 Kelvin. 15,000 to 30,000 expected. A crossing at 122 astronomical units for Voyager 1. A second crossing on November 5, 2018 for Voyager 2. 2 old machines rewriting the edge of the map, and still, the story is easy to misunderstand. Some headlines make it sound like the solar system is ringed by a visible inferno. That picture is wrong. The more accurate picture is harder to imagine, but much richer. It is a dark, thin, invisible boundary where charged particles carry high energies. It is a place where pressure changes, fields line up strangely, and material slips through where a cleaner seal was expected. It is not cinematic fire. It is physics with consequences. That difference matters because fear can make people stop listening. Wonder keeps them listening. And this story deserves wonder. Because what Voyager really found is not just a scary number, it is a living border around our solar home. At about 2/3 of the way through this story, the big, honest turn is this. The models had predicted something simpler. Reality pushed back. Science did not fail there. Science began there. When the universe disagrees with your model, that is when your map gets better. Not faster, not easier, better. The 50,000-degree wall is really a lesson in how nature punishes neat drawings. A boundary can be hot without glowing. A shield can protect while still leaking. A crossing can be historic while still debated in its details. A result can be solid while the reason behind it remains unfinished. That is why researchers do not treat these findings like solved trivia. NASA keeps the mission alive as long as it can. JPL keeps framing the outer boundary as a place of ongoing discovery. Scientists keep comparing what Voyager 1 saw with what Voyager 2 saw. And each comparison sharpens the same message. The heliopause is not just an edge. It is an active interaction zone between the solar wind and the interstellar medium, which is the gas and dust between stars. That phrase sounds technical, but the meaning is simple. Home is pushing outward. The galaxy is pushing back. Where they meet, the pressure leaves marks. Those marks are what Voyager felt. If this kind of careful space story is worth more than a quick scare headline to you, would you leave a comment and say why? That helps me learn which topics matter most to thoughtful viewers like you. And thoughtful is the right word here, because the end of this story is quieter than the beginning. At the start, the idea sounded like a wall of fire. Now it should sound like something more real and more unsettling. A moving shield, a stressed membrane, a boundary that can protect us and still surprise us, a boundary that can be colder than the sun's inner influence and yet warmer than models predicted. A boundary that can align magnetic fields where we expected difference. a boundary that can let some particles through. And all of that comes to us through patient measurement, not from a myth, not from a guess, from NASA mission data, JPL summaries, science papers, Nature astronomy papers, and the work of named people who spent years listening to faint evidence. This is also why the old age of the Voyagers matters emotionally. They are not sleek newcomers, they are survivors. They launched in 1977, outlived fashions, presidents, hardware generations, and expectations. A lot of people wrote the exciting part of their story in past tense. They proved that was too soon. Sometimes the most important chapter begins after the applause dies. Sometimes the oldest messenger brings the freshest shock. There is a kind of poetry in that. A machine built when cassette tapes were normal is now helping define the edge of human reach. Its signal drifts back from beyond the heliosphere like a note from outside the house, not saying danger is here, saying the door is more complicated than you thought, and that changes the way you look at the night sky. Not because every star now seems threatening, because space feels structured. It has weather, pressure, skin, weak spots, and layers. The dark is not empty, it has architecture. The opening image was impossible on purpose, a fever hidden in the cold, a furnace at the edge of winter. At first that sounded like a trick sentence. Now it should sound like a compressed truth. Not literal flame, not the end of Earth, but a real and measured region near the edge of the heliosphere, where plasma can reach 30,000 to 50,000 Kelvin. A place where the sun's shield meets interstellar space and does not do so cleanly. Few people grow up thinking about that border. We all live inside it anyway. That might be the strangest part. The most important walls in your life are not always the ones you can see. Some are made of pressure. Some are made of particles. Some are made of magnetic fields and time. Some are measured by two lonely spacecraft moving through blackness beyond Pluto. So what do we understand now that we did not understand at the start? We understand that the solar system is not just planets circling a star, it is also a vast bubble with a boundary, and that boundary is alive with physics. We understand that the headline number is not a fire alarm, it is a clue that our cosmic shelter is more complex than we imagined, a clue that future deep space travel will depend on getting this boundary right. We understand that old spacecraft can still change new science. We understand that uncertainty is not weakness when it is named clearly. And we understand that home, on the largest scale we have yet touched, is not a wall of stone. It is a moving edge that listens back. Tonight, when you picture the solar system, do not picture it fading neatly into nothing. Picture a great breathing bubble crossing the Milky Way. Picture two tiny machines at its skin, feeling pressure where sunlight gives way. Picture that silent border, hot in numbers, invisible to the eye, and still teaching us how fragile shelter can be. And carry this with you after the screen goes dark. The universe does not stop at the places we once thought it stopped. It keeps going, and so does the need to listen. Sometimes the clearest warning is not a shout, it is a whisper from the edge of home.